Virtual RC Racing. The Inside Story, Episode 3. Developing the Virtual RC Version 3 Physics Engine. Period 2000 till 2005. My name is Peter Barefoots. Before I continue, I must clarify my position in this inside story. I often speak of I and we in this story. At that time, I was still the owner of Serpent, and in this story, I am referring myself as such. Mid-2005, that all changed when I stepped away from Serpent. But my ties with Serpent remained strong, and Michael Salvin remained involved in the physics engine discussions with Todd and myself. I laid out my plans for VRC-V3, not knowing anything about what it would take to develop a proper game or sim. I just had a vast 30 years of experience in RC racing itself, and of course in manufacturing, mainly nitro on-road racing cars, because that is what I had raced myself and was involved in as a manufacturer. With Serpent, we had a few years in off-road with the Serpent Cobra and Spirit line, 1986 till 1990, but that was short-lived, and there was very little product knowledge to go by. The first decision, therefore, was to focus entirely on-road, starting with 1.8 nitro sports cars and 110 200mm nitro sedans. The chassis physics engine was up first. What I had in mind was to create a real nitro on-road racing RC experience with realistic-looking cars and tracks, and even more important, cars that would feel like real RC cars. So two things were extremely important: realistic physics and realistic 3D cars and tracks. Let me briefly explain what a physics engine is and what a physics engine does. A physics engine describes using physics kinematics, and in case of VRC, vehicle dynamics theories, formulas, and data, how an object will behave in a certain environment and react to that environment. In fact, in VRC we have several separate physics processes running at the same time. All these processes combined we call the VRC physics engine. The groundwork for the VRC physics engine was laid with VRC version 3 and was later further developed for VRC-Pro. Next, using the data logger to obtain real performance data. It became clear to me after my first discussions with Todd that for realistic physics, we would need reference data to check the behavior and performance of virtual cars against real-world data. You may remember that somewhere mid-90s, Serpent had developed the DRX 2000 data logger. With this data logger, we were able to record car speed, engine temperature, and lap times. We could also calculate engine power curves by accelerating a heavy roller. The data that we had acquired turned out to be essential input for our physics wizard, Todd "Doc" Wasson. We had very accurate data available about top speed, acceleration, and cornering speed of both the 1.8 and 110 scale nitro on-road cars. And of course, we had a lot of data available from tests at the Heemstede mock track just minutes away. So the first track we developed was the Heemstede track, so we could compare, verify, and match the real and virtual performance of the cars. One of the big unknowns were the tires. We were able to calculate grip levels from car mass and inertias, racing line radius, and cornering speeds by using DRX 2000 data. But Todd already knew that tires' characteristics and physics are extremely complex, as tires don't work in a linear way at all. I'll zoom in on that important part of the physics model in a later episode, as it is a story by itself. Next up was obtaining chassis data from Pro Engineer. Defining the chassis was the first thing Todd went to work on. Obviously, we were going to work with the 1.8 nitro on-road chassis first, because that's where our expertise was and where we had most data of. 3D developer Tony West had already received the Serpent 956 chassis and started to create an ultra-realistic 3D model of it, including the exact layout of the suspension. Todd created a mathematical model of the car by laying out the suspension geometry, defining all the pivot points, the chassis dimensions, and all the physical properties, weight and inertia of the chassis and the complete driveline. How we knew all this? In 1994, we had started to design our Serpent cars using Pro Engineer. This is a so-called parametric 3D design program in which you design each part of a car in 3D. Assign material properties to it made of steel, aluminum, titanium, nylon, etc. And obviously the part was part of the total assembly. Before Pro Engineer, designing a car was a drawing board job and later AutoCAD. But Pro Engineer had changed the whole design process in a dramatic way. Having designed our cars in Pro Engineer gave us access to a wealth of inertia data, which was essential to model the physical properties of a chassis. We knew the exact values of roll, jaw, and pitch moments of the complete chassis, but also of all the rotating parts like the whole driveline, clutch, brake, wheels, and tires, etc. By the way, roll, jaw, and pitch are the three axes a chassis can move around, X, Y, Z, and these inertia moments determine how much it will move when acceleration, braking, and cornering forces are applied to the chassis. They are essential to calculate forces on the suspension, shock absorbers, and anti-roll bars, and ultimately the tires. Without all that data, it would have been virtually impossible to create a model that would behave like the real RC car. To define a chassis and how the suspension geometry and shocks are configured in the chassis physics engine, over 140 parameters are being used. For the on-road cars, Todd had created a 2.5D geometry model, as it was not necessary to animate the suspension. When we decided to create the open-wheel off-road classes, that was in 2010, Todd had to create a whole new 3D geometry model. Next up was the engine physics model. We had a lot of data from our engine power and torque curves, but rather than to use these power and torque curves, Todd was convinced that it would be better to model the engine itself. That was quite a challenge considering the complexity of how a two-stroke engine works. Todd knew it was necessary to develop a complete engine physics model if we wanted to be able to set the mixture, calculate fuel consumption, play with fuel, oil, and nitro percentages, know when the engine is overheating, select the correct glow plug, and more. I thought it was impossible to do, but I soon found out that Todd was determined to take on this big challenge. I remember he worked on the physics model for these small two-stroke nitro engines for more than 8 months, and amazingly he delivered a brilliantly working physics model to simulate a real nitro two-stroke engine. Never thought that was even possible. In the two-stroke engine physics model, all the intake and exhaust port timing is included, bore and stroke of course, and the exhaust system, so critical for a two-stroke engine. Compression ratio, carburation, fuel mixture, glow plug heat factor, you name it, it's all in this physics model. Over 80 parameters or variables. And when you run the car, the engine performance is calculated real-time using all these variables. 350 times per second. Hard to believe, but it's true. And for the exhaust system or tuned pipes, Todd defined another 10 parameters which allowed us to configure different engine performance characteristics. If I think back of it now, simply amazing. And last, the aerodynamics physics model. As we all know, aerodynamics play a very important role in cornering and top speed performance, but we had no aerodynamics data available. We had done data logger tests with and without body, and this gave us a pretty good idea of downforce levels, but it was just an estimation. As we had no means of testing different bodies ourselves, we approached the Technical University in Delft to see if they would be interested in setting up a program to measure 1/8 and 1/10 scale bodies in their wind tunnel. TU Delft is particularly known for its aerospace studies, so this was the right place to go to. The data which was acquired was limited, but good enough to give us a good indication of downforce and drag levels. We had already decided that we were not going to apply big differences between aerodynamic properties of bodies, because we would then surely end up with everybody using the same body like in real RC racing. In other words, only the body with the best aero properties would be used. All we did was create variations between downforce and drag levels depending on the class and scale. In the next episode, I will zoom in on the tires physics model. As I said before, a story by itself. Thanks for watching.